Hi, this is Mr. Waite. Today I'd like to talk about populations and how that relates to ecology. First thing I'd like to look at is Darwin's famous elephant problem. Darwin made these observations on elephants, and he tried to do some mathematical calculations about how many elephants would be produced from one breeding pair. And so it tells us right here, it says, assuming that an elephant breeds when they turn 30 years old, and they go until they are 90 years old. They bring forth 3 pairs of young during this time. By the end of the 5th century, there would be alive 15 million elephants from this one population, descending from this first pair. This is the type of growth that Darwin was talking about. Here's your original breeding pair. The current population, if they continued to reproduce at this rate with no deaths in the number of babies being born, eventually we'd get enough elephants to cover Africa. If we keep going with that, we'd get enough to cover the entire surface of the earth, and eventually enough elephants to be stacked 1 kilometer deep across the surface of the earth. Now, obviously that doesn't happen. In fact, the famous physicist William Thomson pointed out how Darwin's calculations were wrong, and that instead of 15 million elephants in that time period, we would actually only see about 16,000. But the question arises, why do populations not continue to grow and grow at this same rate? And what is limiting that population growth? And that's what we'd like to look at today. So the first thing we're going to look at are this idea of distribution, or another way I can think about this is movement within populations. And how are populations going to move about? They're going to be affected by the biotic factors, or the living things. They're also going to be affected by the abiotic, or non-living parts of the ecosystem. The next thing we'll look at is, how do populations grow? We have 2 growth models we're going to analyze. One is the exponential growth model, and the other is the logistic. And finally, we're going to look at population density. What is going to regulate the density of a population? And we're going to look specifically at density-dependent factors. We're also going to look at what keeps the density from, or what keeps it changing all the time. And we'll look at predator-prey relationships. So the first thing we're going to look at is this idea that organisms are affected by both biotic, living, and abiotic, non-living factors. Examples of biotic factors would be a predator-prey relationship that we see right here with the cheetah and the zebra. This is an example of predatory behavior. There's also herbivory, where we see the zebras would be eating the grass. The elephants rely upon the tree. But the idea here is that these biotic factors are living factors, or how do organisms affect other organisms? Versus if we look at the abiotic factors over here, these are the things that are not living that will still affect the overall population of particular individuals. For example, if this were a canyon right here, the sun is going to shine and hit this side of the wall, making it pretty warm on this side. That's going to make it kind of more dry. And it's not that the sun doesn't hit over here, it might hit indirectly, but not directly like we see over here. So over here on this side, we expect it to be cooler, probably a lot more grasses or trees and shrubs growing over here on this side. So temperature is one abiotic factor. It's important to know that proteins usually denature around 45 degrees Celsius. The other types of abiotic factors are water and oxygen, or the lack of. We also have things within the water. The amount of salts inside there determine the salinity, and other things like soil and the rocks. And when we look at those, we look at their mineral composition, also their pH. All right, the types of growth that we're going to see when we analyze populations. One is an exponential growth. And when I talk about exponential growth, I like to point out to my students, these typically have a J-shaped curve associated with them. Obviously, this one's growing at a much faster rate than this one is over here. But this is your idea. Again, we're looking at a J-shaped curve. Exponential growth is really where a population growth increases under ideal conditions. There's nothing really limiting the growth rate of that population. That's to be contrasted or compared with logistic growth. So again, here was our exponential growth that grows like a J-shaped curve, but over here in the red we have a logistic growth. And I like to say this sometimes appears as more of an S-shaped curve. So logistic growth has this S shape associated with it. What it means is the population doesn't continue to grow and grow and grow. We're eventually going to run into this point where it stables out and we're not going to have any more growth. What we call that point is our K, or our carrying capacity. In other words, there probably aren't enough resources to continue to feed any more individuals, so the population's going to stay at this rate unless we see fluctuations, which we'll talk about here in just a little bit. So when we look at these, I wanted to look at a practice problem. This one says a population of fruit flies exhibits logistic growth. So if I know it's logistic growth, I come over here to my AP Biology equation sheet and I identify the equation for logistic growth. Before I go too much farther with this problem, I do want to point out the AP Biology equation sheet gives you so many equations, but the nice thing is that they look confusing on the surface, but if you look over here, they tell you what each of these symbols means over here. And so if you can identify the variable that they're talking about in the problem, you can usually just plug that in to the equation and solve for it. Let's keep going with this. The maximum population growth rate occurs when the population is 250 individuals. So I know my population size, or N, is 250. If the carrying capacity is 500 flies, here's the carrying capacity, 500, and the R max, and it tells us here, the R max is the maximum per capita growth rate of the population, that is 0.1. It says what is the maximum population growth rate for this population. Now, one thing I need to point out over here is whenever we see this dn over dt, dn over dt, dn over dt, that's what they're talking about, this growth rate right here. So a lot of times students get confused. They say, what should I plug in for d? What should I plug in for n? When in fact, this is what you're solving for. This is going to give you the answer. That d stands for delta. So change in n, which is the population size, over the change in t, which is time. That is going to give you the population growth. Another thing I always try to stress is anytime you have something that is change over time, that represents rate, and we need to refer to that as rate, especially when we're answering FRQs. So let's go ahead and solve this problem over here really quickly. Let me get some room down here. I'm just going to copy this equation, and I know that I'm solving for dn over dt, so I don't need to plug anything in for that. But my R max is given to me, so my R max was 0.1. My N, population size or number of individuals, is 250. I'm going to multiply that by what's inside the equations here. My K is my carrying capacity of 500. My N again was 250. I'm going to subtract that. And I'm going to divide that by K, which again was 500. If you put this into your calculator and you follow the order of operations, the answer that you should get from this is 12.5. And if we look at the units on this, we're looking at flies, or excuse me, individuals per month. So this one, proper units would be individuals per month. So that's one type of problem that you see. Another type of problem might look something like this. These are called age distribution graphs, and they describe the ages of the individuals in a population. So you can see we have three here. This would be, that represent three countries: Kenya, Nigeria, Saudi Arabia. Over here we have places like Australia, Canada, the US, and Austria, Denmark, and Italy over here. The first question asks, which countries are experiencing the most rapid population growth? If you look at this closely, you'll see that there's a small older population here, a relatively large medium one, and a very large group of individuals down here that are between the ages of 0 and 14. So obviously there will be some deaths, but if the death rate were very low, these individuals continued to age at the and grow older. They're going to go like this. Eventually, instead of a small population like this, we will have a large population here. So which one's experiencing the most rapid growth rate? Kenya, Nigeria, Saudi Arabia. The next question asked, it says, which countries will have a problem caring for their elderly population? Well, if you're not prepared for, if you have a small elderly population and all of a sudden in a few years' time it becomes a large elderly population, it's going to be the one that's experiencing the largest or the fastest growth rate. Over here, next question asked, why is Saudi Arabia's graph so different from Italy's? And what you can see over here in places like Italy is they have almost zero growth rate right here. Very few individuals are being born compared to the amount of individuals that are being born over here. Another thing we're going to look at are the density-dependent factors that regulate population sizes. One thing we may not think about are the physiological factors. These include things like how much room do the individuals have around them, and is this going to affect them, how does this affect them on a day-to-day basis? Basically, what we're looking at with this one is the physiological factors. Reproductive rates can drop, especially when there's a high density and aggressive behaviors associated within the individuals in this population, or there could be hormonal changes as well. Obviously, predation is going to be one that the more predators you have, that's going to affect the population, or the more prey is also, it's going to be easy for the predators to access that prey. We'll talk about that shortly here. Disease is very dependent upon a population. One individual gets that, they can share that disease with other individuals within the population. An unfavorable environment, that's not going to help a population at all. Territoriality. Now, I like this image here because it's showing how this cheetah marks its territory. There are chemicals inside the urine that allow the cheetah to tell other cheetahs in this area that, hey, this area belongs specifically to me, so you need to stay away. Therefore, it's going to regulate how large that population can become. The last one is populations. This isn't a great picture, but competition. And this is more competition for resources, maybe not a horse race, but the fewer resources there are, obviously, that's going to regulate how quickly or how much the population can grow. One of the last things we're going to look at is this idea of predator-prey relationships. So obviously the gazelle down here is the prey, the predator is the lion, and what we see is if there's a low population of lions or predators, that allows the prey to increase dramatically. Eventually, we're going to have, they're probably going to reach their carrying capacity as far as resources, but during this time, the lions are going to be able to feed upon them, the predators feed upon their prey, and as that happens, they're able to flourish and reproduce fairly rapidly. But what we see, the prey tends to start going down. When the predators go up, the prey goes down. So we see this almost inverse relationship between predators and prey. And that's pretty much everything we need to know about populations. Over here, there's just a quick little movie I put in here. I'm going to see if it works. All right, that's populations. I hope that's helpful, and we'll see you next time.